Hello everybody and welcome to exercise 6. Let's take a minute just to read this exercise together. So they're giving us a linear transformation T that goes from R5 to a vector space W. They're telling us that the rank of this linear transformation is 2, and they're giving us some vectors, u, v, and w, telling us that they form a linearly independent subset of the null space. They'd like us to prove that with all of that information, this set beta, which involves various linear combinations of u, v, and w, is a basis for the null space. Okay, well, to show that beta is a basis for the null space, we first really need to know that those three vectors are in the null space. So how about if we start off our proof by just illustrating that before we get into the other details of the problem. Okay, so there we can use the linearity to kind of convince ourselves that those vectors really are in the null space. So first, we're going to observe that since T is linear, okay, we have T of u minus v equals T of u minus T of v. And they tell us that u and v are both in the null space. Okay, that's this sentence here. So we know that T of u and T of v separately are both 0. I'll write the 0 vector as just 0v. Okay, which confirms that u minus v is in the null space. And you could use a very similar argument to convince yourself that the other two vectors up here, those are also in the null space. So we won't do that, we'll just remark that we could do that similarly. So we've just confirmed then that this set beta really is a subset of the null space. Okay, so it at least has a chance then of being a basis for the null space. Okay, now let's think about what's involved in showing that a set is a basis. It seems to me that a basis has two properties. It needs to be linearly independent, and it needs to span the space that we're talking about, in this case, the null space. Okay, and as I've always said, I encourage laziness in mathematics whenever possible. So I'd like to do this in the most efficient, laziest way that we can. Do we really have to prove both of those things, the span and the linear independence? We can actually get away with just proving one of the two things if we can first figure out what the dimension of our null space is. Okay, so that's going to be my next step here in this problem. Let's use the dimension theorem and see if we can figure out how big the null space is. Okay, so by the dimension theorem, we have the dimension of the null space is equal to the dimension of the domain, which in our case is R5, minus the dimension of the range. But notice that in the problem, well, first of all, we know that the dimension of R5 is 5. They told us that the rank of T is 2, and the rank, by definition, is just the dimension of the range. Okay, so that's 5 minus 2, which is 3. Okay, so we've just calculated the dimension of the null space and determined that it's 3. So that's a good sign because we're trying to show that this set that contains 3 vectors is a basis. Okay, so here's how that statement helps us. Since we know that the dimension of the null space is 3, all we really have to do is to show linear independence. That's going to be enough to show that this is a basis by the famous corollary 2. Okay, so let's put that into words here. If we can show that beta is linearly independent, it will follow from corollary 2 to the replacement theorem that beta is a basis for the null space of T. Okay, so all we have to do is to prove linear independence here, and we'll do that directly from the definition. Okay, so we're going to start with a linear combination of these vectors, set equal to 0. Okay, and in our case, let's just take a peek what our set was again. So it had these three vectors in it, so we want to form a linear combination of those three vectors. Whoops, that's not V, it's U. Okay, U plus W plus C3 times V minus W. We're going to set that equal to the 0 vector. And what we're trying to show is that that equation, let's give it a name, I'll just call it star. We want to show that that equation has only the trivial solution. In other words, we'd like to show that all three of those constants have to be 0. Okay, so rearranging okay, in other words, if you just kind of take those constants and distribute them through and just regroup, you are going to get, or another way of writing this looks like C1 plus C2 times U plus negative C1 plus C3 times V plus C2 minus C3 times W equals the 0 vector. Okay, and again, that's the same equation as star. We've just rearranged it so that it looks like that. Okay, now why did we do that? Okay, well, the key is we know something about these three vectors, U, V, and W. We were given in the problem that those vectors are linearly independent. So what does that mean? Well, it means then, since this is a linear combination of U, V, and W, that the three constants, the scalars that I'm underlining, they all have to be 0. Okay, so since, and let's see, what did we call that set? I believe we called it L. So since L is linearly independent, okay, we have C1 plus C2, negative C1 plus C3, and C2 minus C3, those all have to be 0. Okay, but we're really talking about a system of equations. They're a system of 3 equations and 3 unknowns, and if we solve that system for C1, C2, and C3, you can probably guess what's going to happen here. We're going to get 0 for all 3 of those constants. Okay, and so you could do this in a various number of ways. You could put this into a matrix and do it that way using row operations, or I kind of noticed here that if you add these equations together, nice things happen. So adding these 3 equations, okay, so C2 equals 0, and if C2 equals 0, well, you can kind of look at this. That's going to force C1 to be 0, and then C3 is also going to follow suit. So just a couple of short steps, and we've got our solution in this case. So the first equation okay, and then if you move on to the third equation, now that we know that okay, well, at this point we have C1 and C2 both equal to 0. Okay, so actually the second equation, if we look at that, that's going to tell us that C3 is 0. Okay, and so if we just kind of take stock of where we're at here, Okay, we've demonstrated that C1, C2, and C3 are all equal to 0. If you go back up to equation star, we've just demonstrated that equation star has only the trivial solution. That's exactly what it means for the three vectors to be linearly independent in star. And that's really what we wanted to show here. Okay, so let's just put that into words. Equation star has only the trivial solution. Okay, and so the set beta is linearly independent. And by the remarks that we made above, that's all that we need to show. We already showed that the dimension of our null space is 3, and so put that together with the linear independence, and we are done. So by our previous remarks, beta is a basis. Okay, and we're done.